Oh, hey guys, what's up? Eddie Aho here with KissAnalog.com. Hey, I'm sitting next to a whole bunch of, well, several isolation transformers. These are kind of special ones. And this is kind of a project I started a long time ago. Variac. Let's talk about that in a moment, okay? Here, isolation transformers. What are they? Okay, guys, I'm going to pull up my iPad here. And let's draw an isolation transformer, okay? We're going to have a primary winding. Have some turns on there. And then we have an iron core. We have some kind of core, so we have to show the core. And we have secondary windings. Okay, that's a transformer, right? It's an isolation transformer. It's galvanic isolation. Why? Because what that means is you can put an ohm meter on one of those windings over here, and I'll just call this X1, X2, we'll call it X3, and X4, okay? So I can put an ohm meter on X1, X2, and then put the other lead on X3, X4. I don't read anything. High ohms, right? Isolation. It's isolated from the secondary side. So a primary current flows through the primary winding. I'm going to get rid of the names of those things because we're going to call them something else in a moment. This is a primary side and a secondary side. Okay, primary current flows through there, builds a magnetic field, couples onto the windings on the secondary side, puts out a voltage. If it's 1-to-1, we get 120. Say we have 120 turns on the input, 120 turns on the output on the secondary side. Each turn is 1 volt. Let's say 120 volts. We got 120 volts on the secondary side. Okay, 1-to-1. So sometimes that's shown as a ratio. It's like 1-to-1. Okay, a 1-to-2 would be a step up, or 2-to-1 would be a step down. But say we have a 1-to-1. Okay, now I'm going to put a box around our transformer. Let's see if I can do this. We're going to put a box around this. That's our isolation transformer, okay? But you know what? I have 3 prongs on both the input and output, so I'm just going to show that. So, and you know what? What I'm going to do, change colors, and we're going to put this as a green one, okay? And we're going to do a chassis connection. So pitchfork, that's a chassis symbol, okay? That's a proper one. And then on the secondary side, we're going to have same thing. We're going to have a third wire coming out, so that's going to be connected to chassis as well. So they're essentially tied together. They're both tied to the metal, okay? Now, here's the thing. Here's the power on the wall, or through my plug strips or whatever, okay? On the other side, we're going to have a green wire too, right? And then we're going to have our other 2 conductors. And I'll just separate them like this. And one's going to be called line, one's going to be called neutral. And the reason it's called neutral is because at the surface entrance, it's bonded to ground. So the neutral one we know is on the low side, reference to ground. Ground is a very, very confusing term. Crazy. I kind of hate it. I hate that we call it ground, because it really doesn't have anything to do with earth ground. But let me explain something here. This ground, these chassis connections, all metal things are going to be grounded to chassis, same connection, okay? The same green wire. So the 3 prongs, that ground connection, first thing it does, it goes right to chassis. We want all the chassis connected together so they're all the same potential. We don't get shocked when we touch one chassis and then grab another chassis. All same potential. So we always want that. We want that in our isolation transformer too. So the 3 wires coming in, we want it hitting this chassis, okay? Now here's the thing. If you're one of those kind of guys that likes to go barefoot on wet concrete, well, then, the grid system out there, the power system, they tie ground rods and they bond the neutral to ground on their transformers on the primary side, and they all take them to earth ground, okay? And so here, let's draw that. So we have this bonding connection to our ground rod, and that's earth ground, and that's the earth ground symbol, okay? All right, and you'll see that drawn different ways, circles around it with an S or safety ground, things like that. But okay, so that's our power coming into the house. Only at one point do you tie neutral to ground, okay? And that's at the service entrance. That's where the power comes from, the power system, you know, provided to our home or to the building or whatever. They bond it there at one point, they put a ground rod in. So now the ground, the earth ground, that concrete, that wet concrete that we like to stand on when we're playing with electricity, it's all connected to our chassis. We're all at the same reference point. We're standing on things, touching things. It's all the same voltage potential. We're all safe. That's the number one thing, safe. Now, we don't want any current flowing in that green wire, in that third wire, in the earth ground. We don't want any current flowing. The grid system, you know, it's tied to earth ground, Mother Earth, which is a very poor conductor, but it's tied to Mother Earth just to give some kind of reference point. It just turns out that, hey, by chance, you know, that dirt does carry a little bit of current, so it is some reference point, even though it's not a very good one. It's a reference point. So it's kind of like these anti-static mats that we put on our benches and that. If we do it right, we'll have a little ground strap going from this to that grounding, that chassis grounding system, the third prong, you know. We'll take that to that ground system, okay? And that's so that if we're working with things, everything's all at the same potential. Our soldering iron, all that stuff's all grounded. And then we put that wrist strap on, right? But you know what? In that wrist strap, there's a resistor, like 10 mega ohms. So what that does is you're bonded to the ground system, but through a big resistor. So that means that, you know, you're not going to have a lot of current going through you to the ground because that big resistor. But what it does do, though, is that static electricity, it's not going to have a chance to build up on you because that resistor is going to leak it off into the ground. And that's what all those ground rods, all in the power system, it just gives it a nice reference point, and it just leaks everything off so that this floating power system just doesn't float to some gigantic potential and then, like lightning, all of a sudden want to hit the earth and you know, neutralizes itself. So, but if lightning does hit the power grid system, the ground rods say, hey, come over this way. Don't go through all those wires and melt them and cause fires. Come down this way. And it will try to protect those transformers from stepping on that high voltage down to a lower voltage that comes to our house, right? And then when it comes to our house, same thing. They'll put a ground rod in. They try to put everything, neutralize everything, put everything in the same plane. You don't want any current flowing through there. It's not a magical earth ground place where noise and all this stuff goes to. No, it's just a place to reference things to. So they all kind of have the same reference. These metal chassis, they're all tied together. That's a much better grounding system. But it's also called safety ground because now if the line touches the metal, then there's a fault current, and the current comes from the line conductor into the chassis, into the green wire, the third conductor, and back to the breaker and pops the breaker. Well, let's say, I mean, they did that back in the 50s, I think it was. Let's say if they would have just taken one of those two wires, the neutral, and we would have called it a neutral, let's say. Let's call it hot and cold. I don't know. You could have called it anything. But that neutral wire, they could have tied it to all the metal. So all the metal chassis are all neutral. Good. It's all neutral. The problem is if, let's say something over there is shorted to chassis, the line shorted to neutral, to the chassis over there, well then that high current can go through all these chassis connections, finally back to the neutral, and then back to the breaker and pop it. But the problem is now you got this heavy current flowing through all these chassis. it doesn't have that third green wire just to jump on the green wire and shoot back. So the third wire makes things safer because it doesn't carry any current unless it's carrying fault current. Unless there's a fault, then it has, hey, now I'm in play. I'm going to give you a place to route the current back to the breaker because it's tied to neutral way back there. And so it jumps down on the green wire, shoots across, pops a breaker. Okay? So just to straighten that whole concept out. So we want these chassis tied to that same thing. We want them all to be the same potential. It's a safety thing. All right. So the secondary side, we got a 3-prong plug. Well, a lot of equipment has 3-prong plugs. If there's metal chassis, they're going to have a third prong because that's part of the rule, is to make all your metal chassis the same potential. So you provide that on your isolation transformer right here, right? So it comes out and it goes back to your chassis right here. This is a pitchfork, okay? So it goes right back to ground. Problem is if you have a fault, like say we're going to call it X1, X2. If you have X1 or X2 short to the chassis, what happens? Nothing. Because there's no path for current. X2, let's say X1 here gets shorted down here to that chassis. Well, nothing happens because the path through that secondary winding goes out X1, off into your load, comes back to X2 and circles through. Oh, but it also touches your chassis. Well, where does it go? There's an isolation transformer. It can go back to, it's touching the same place that the neutral and ground are bonded back there. If you ohmed them, they'd all have the same place. X1 would be ohmed to your neutral on your primary side. But the isolation transformer is still isolated. Okay? Isolation means that the power on the secondary side is still isolated from the primary side. And if you take an ohm meter, well, okay, now if you take it to X1 to neutral, you would see some ohms there, right? It would be connected. But there's no path of current flow. So X2, if it touched the housing, then you would cause a short and it would pop the breaker, right? All right, so now here's the thing. What if you have a 2-prong device, an old 2 amplifier, an old tube TV or something like that, something with just 2 prongs. If it's back in the day, those prongs are the same size, narrow, both narrow. They didn't have a wide and narrow because they didn't have neutral line and ground. They just had line 1, line 2, or X1, X2, that kind of thing. So this transformer, the way I'm showing right now, it shows that the secondary winding is just floating. It's not referenced to anything, right? So if you went, well, you know what? I want to recreate what I had at the other side. Whatever device I plug into this thing, I want it to have a place where it pops a breaker if something touches this. Because if something touches it, I want to know it. I want it to pop a breaker. I don't want this thing to have some, I don't want it to be connected to that winding voltage. Okay, so what you do is you come and say, okay, let's bond it. Well, you know what? You recreated this bond thing. So now instead of X2 and X1, instead of these things, now we'll call this line a neutral. It's a different line of neutral, so maybe call it line 2 and neutral 2. Okay? So now if line 2 touches this, we pop a breaker. Let's say we have a fuse or a breaker inside this transformer, or even on the outside on that line. So now it pops a breaker. But most often when you think about an isolation transformer, you think about having a floating output that's not referenced to your ground system. And that way, if one of the wires or the other wire touches it, then it's okay. If it does it by accident. Or if you touch it by accident. So if you're touching this and then touch your chassis. Here's the thing. If you're doing an old tube amplifier, it could be, here, let's go backwards on this. I'm going to get rid of this stuff. Okay, if you hook up an tube amplifier to this power system, that winding's floating, right? Now that case, it's probably tied to one of those, one of those two pins, one of those two prongs on the power cord. And that's so that it's just all referenced to the same thing. So you don't know which one is there unless you ohm it before you power it up. You don't want to ohm it when there's power on it, but you ohm it and you go, okay, this pin is tied to the chassis. Well, that pin, if it was tied to a line voltage, now that chassis is hot in reference to neutral, right? So now it's got two prongs, so you can plug it in either way. One way it's the housing's neutral, the other way the housing's hot. So that could be an issue, because you might think all your metals are all tied to the same thing, not realizing that the two prong doesn't know which way it's connected. So you could touch that and touch something that's tied to chassis and to neutral, and you get a shock there. The other thing is, here, let's draw a scope. Okay, I've got my scope down here, and here's my display, right? There's my display, and here's my 4 channels. All right, now I hook a scope probe up to that, okay? But really, it comes off to a scope tip, right? I'll draw the tip like that, and then it has a little strap for a ground strap, right? We call it the little ground strap. So let's say it comes off like this, and this is my little alligator clip, okay? So that thing is tied to the chassis, because on these scope probes, on these scopes up here, the BNC, it's metal. Anything metal you can touch should be tied to the same potential, which is chassis. So in this case, on this isolation transformer, well, let's go to the primary side, okay? If I touch that green one to neutral or to chassis, it's fine, because that is the same connection point, right? But if I tie it to line, now I just shorted those, that's bad. On the secondary side, if I had that bond, I'd have same situation, right? But since I don't have that bond to chassis with my winding, it's floating. Now I can touch that to either X1 or X2, it doesn't matter. It's just floating. Now I've referenced it to my chassis by doing that. Now, let's say if I tied that to X1 and I put my scope tip on X2, I'd see 120 volts. Everything would be fine. But the thing is that chassis, X1, is now tied to the chassis system because of my scope. It's okay unless you make another other connection where you get a circuit, right? So you just want to be aware of that. So if you're testing, if you got a test bench and you want a floating output because you know that's what you want, then make sure that bond is not there. Alright guys, so on an isolation transformer, usually you just don't want that bond. You don't want this bond in here, okay? But you might want it. So you have to decide for yourself if you do want that. If you have a 3-prong device you plug in, you still get your safety ground. The chassis, like almost every piece of equipment that has 3 prongs, it's going to have capacitors, right? Here, let me just draw more here. You're going to have a capacitor from line to chassis, and you're going to have one from neutral to chassis. That's just part of the EMI filter, the Y capacitors they call them, right? Y capacitors, because they're from line or neutral from one of your 2 conductors to chassis, to ground, to earth ground, to safety ground. There's so many names, and depending on how you use them and how you think about it, it's just confusing. But they're tied to the chassis, okay? And so if your chassis is floating, like I've been in labs where on an oscilloscope, so do those cheater plugs, the 3 prongs to 2, and they do that so they don't have any potential issue blowing up their scope. They have to be careful because now, you see the 2 chassis connections? It's just floating. The chassis is floating, right? But now you have 2 capacitors in series from line to neutral, and the center point is chassis. So it's a voltage divider. So if you had 120 volts, you basically have 60 volts at your chassis. So now your chassis is floating around at 60 volts. Okay, so yeah, just have to be aware of that. It's not, you know, I don't want to condone floating a scope or anything else. You know, not using that third one. But anyway, that's a potential safety issue, right? So you got to be careful. 3 prongs, the reason they use them is to tie the chassis to so they're all tied together to the same potential. And then that way those capacitors, they get leaked off. There's a little bit of leakage current, and you know, it's floating around. So, but it's minimized. There's a max amount of leakage current you can have. Okay, so the capacitors have to be minimized to a certain value. Okay, but when you have a 2-prong device, you can plug it in here. Now, even if you had the bond over here on the secondary side on a 2-prong device, and you plugged it on a 2-prong device, if you plugged it in, it wouldn't matter, because I mean, it wouldn't matter for the equipment. The equipment wouldn't care because it has power through the winding. One of the pins or prongs or whatever is referenced to chassis ground, and it's like, well, I don't care. There's no current flowing from the secondary side back to the primary side, so it wouldn't care. But it's only when you introduce a second piece of equipment that is also a 2-prong device that has the chassis connected, you know, maybe the chassis on each one, they're connected to, there's a prong on each one of them connected to the chassis of these 2 devices, but they're opposite pins. You wouldn't know that because there's no keying. Without that third pin, the ground pin, it's not keyed, right? Now, newer 2-prong devices, since line, neutral, and ground have been developed, the 3-prong devices, now if you get a 2-prong device, one of them is wide to try to force you to put it into the neutral side. So they try to say, okay, so if there was a reason that one had to be polarized, we would know that, you know, we'd know which side was not line and neutral. But I don't know if you can ever count on that 100%. So you got to be safe. You got to be careful about that. Even 3-prong devices, people can wire them backwards, so you got to be safe about that. It's good to use those little plugs to check them. I was just looking for one. I have one back here somewhere, but you know, you want to use those to make sure they're polarized correctly, right? So that's the thing, guys. The transformers are still isolated from primary to secondary side. There's no current flowing from primary to secondary, or vice versa. But let me show you one other thing you have to be aware of. There's a capacitor, it's called a parasitic capacitor, capacitance, inside the transformer. So even though you don't have a connection, here, let me get rid of that bond. Okay, they're not bonded together anymore, right? Okay, they're not bonded together anymore, right? But the thing is there's a capacitor, there's capacitance between the windings. The windings could be laying on top of each other, wound on top of each other. There'd definitely be capacitance between them. But also, the primary winding wound on a core, it'll have capacitive coupling to the core, and then the core will have capacitive coupling to the secondary winding. So that capacitance might really be just 2 series capacitors in there. The winding, one winding, primary winding to the core, and then the core to the secondary winding. But so you have capacitance from primary to secondary. So even though you don't have, you know, you got magnetic coupling, right? But also you have capacitive coupling. So you can have voltage potential on your secondary side because of your primary side with that capacitance. And you can discharge that capacitance into you if you're to touch the wrong thing, you know. So anyway, you just have to be aware of that. So that's why this one's called an extreme isolation transformer. Very low capacitance. This one's an ultra, another name for it. They have very little capacitance. They purposefully try to minimize that capacitance as much as possible, so there's no leakage currents from the primary side into the secondary side. It also helps reduce noise. So that's another reason why these isolation transformers are actually still good to plug a oscilloscope or some other device into, because they can isolate the noise and stuff to that oscilloscope. So that's still a nice thing to do, is isolate your oscilloscopes for that reason. Now the oscilloscope, everything, all the metal, still all tied chassis. Remember that. So even though you isolate your scope through one of these, that BNC connector is still tied to the same point that it was before. They're all tied to chassis. So you got to be aware of that. Even if you don't have the bond on the secondary side from one of the pins, from one of the winding pins to chassis, that scope still has the BNC connector tied to chassis. So just be aware of that. So I hope this made some sense. I hope this helped clear up some things. I watch a lot of YouTube videos myself, and I've watched some things on isolation transformers. Sometimes people say, well, it's not an isolation transformer because the grounds are connected. It's like, well, it's still an isolation transformer. It's just a different way to wire the primary, secondary, and there's different reasons why they would do that. If they bond one of those winding outputs on the secondary side, like say that X2 to the chassis, and create that, you know, bond point, recreate that bond point from your surface entrance, because they go, okay, we isolate it, but we isolate it for noise, for other reasons, but we still want our ground and our neutrals to be bonded together. So if there's a reason why they did that, you want to be aware of that. And so you want to take an ohm meter between the ground pin and your other two pins to see if they are bonded together, or open up the plate and look inside. But a nice way to do it, because maybe you look inside, you don't see it, but if you ohm it, you'll know for sure. Okay, it's nice to do both, you know, but maybe it came loose and it's flopping around inside there. That's not a good thing. I'm going to take this one apart. This one has had trouble, so we'll see in another video where I'm going to take this one apart and rewire it, and I'll take some scope waveforms and stuff like that so you can see what it looks like, okay, from primary to secondary side. All right, so hopefully that'll be helpful. So these are hospital grade, meaning they have high isolation between primary and secondary. They have very low leakage current. So like this one has extreme, this one's ultra. This one doesn't have any stickers or anything on it. I think it came with some other device probably. I bought these in the flea market back south, so I can't really remember where exactly. But anyway, hospital grade, low leakage, that kind of thing. Really nice. And you have to check to make sure that you have that floating secondary winding that's not referenced to chassis. Still an isolation transformer. It's just the ground. And the ground on both sides, if you do have three prongs, the ground on both sides will still be the same ground. But the real thing you want to look for, the key difference, is if they bond that ground to one of those two conductors on the pin, okay, on the connector. So you want to look for that. This is a Variac. I started this project years ago. I got to finish it up. But anyway, this Variac, it's not an isolation transformer. Variacs are not isolation transformers. So your Variac, it's wired totally different. Here, let me show you. It has a winding like this, right? And you have line, neutral, okay? But then what they do is on the secondary side, where you take your power off, you have neutral, and line here is a wiper, okay? That wiper goes up and down, and if it goes down towards neutral, it's 0 volts. If it goes up towards the top, it's 132 volts or 120 volts, okay? But what if, sometimes what they do is they add some extra windings, okay? So if it goes up, it can actually go to 130 or 140 volts, okay? That's actually fairly common. So on the secondary side, you can go up and down voltage, and it's kind of nice because it's very nice. So when you're testing things on AC power, it's really nice to go through an isolation transformer, but then also to go through a Variac so you can bring up voltage slow. I have the AC power supply back here from iTechnologies, which I love that thing. So that's amazing because not only is it like a Variac, but it also has a current limit on it. So super nice, and it's actually an isolated AC output. So it regenerates AC isolated, so it kind of does these two things combined. So very nice. All right, guys, hope you liked it. 2 thumbs up to my Patreons. appreciate you guys. 2 thumbs up to Danny, my team member on YouTube, and to all my YouTube members. Really appreciate you guys. You become a member by clicking the button below, or a Patreon member by looking at the description in the video down below, for as little as $1 a month. And you can also support the channel for free just by liking the video, you know, sharing it, subscribing. That's awesome. Thanks for watching, guys. Really appreciate it. Let me know if this is helpful. Hopefully it wasn't more confusing. The word ground is just covers so many different things. You know, on DC power supplies, we have a red and a black, so we think of it as hot and return, or as hot and ground. But then there's this green terminal in between. It's a chassis ground, because again, metal box, they're all tied to chassis. You could take that green, tie it to red, so you have a negative voltage out, and your positive is referenced to chassis, to ground. But we always think of ground as the return point for our current, but then when it comes to AC, or chassis protection, safety protection, ground is the chassis. So it should be just called chassis ground, right? So anyway, you can take your black to chassis, and then that way you have a positive power system, so in reference to your chassis. All right, hope this is helpful. Thanks for watching. Thanks for staying tuned, and we'll see you next time.